An m by n matrix A is a rectangular array of real numbers with m rows and n columns. M and n are the dimensions of the matrix. The numbers that appear in the matrix are called entries. Typically, we use capital letters to denote matrices. So for example, matrix A has 2 rows and 3 columns, so it's a 2 by 3 matrix. Row 1 has entries 2, 0, and 1. Matrix B has 4 rows and 2 columns, making it a 4 by 2 matrix. If you want to refer to entries in the matrix, then you refer to the entry in the ith row and jth column as the ijth entry. So for example, A22 is negative 22. B41 is going to be 8. B32 is going to be 3. Two matrices A and B are said to be equal if they have the same dimensions and the corresponding entries are the same. So for example, if I have a matrix A and a matrix B, as in this example, the two matrices are only equal if the entry in the first row, third column of A, our value of x, is the same as the one in the first row, third column of B, 0. So x has to be 0. Similarly, y plus 1 has to equal 11. So y is equal to 10. A matrix with a single row is called a row matrix or a row vector. A matrix with a single column is called a column matrix or column vector. A matrix with the same number of rows and columns is called a square matrix. So in my examples here, I have a 1 by 5 matrix C. That's a row matrix. I have a 4 by 1 matrix D. That's a column matrix. Matrix E is 3 by 3. And because the number of rows are the same as the number of columns, it's called a square matrix. We can add or subtract matrices only if they have the same dimensions. Adding and subtracting is done component-wise. That is, if you look at the sum of two matrices A and B, what we're adding is the entries that are in the same position in each matrix. So in the example here, 2 plus 1 is 3. So adding the components in the 1, 1 position of each matrix gives us the sum of 3. Next, we'll add negative 3 to positive 1 and get 2. We'll add 1 to negative 2 to get negative 1. And we'll add 0 to 1 to get 1. Here we've got a couple of examples. In the first example, we're going to add two matrices. Since their dimensions are the same, we can go ahead and add each entry. So 2 plus 9 gives us 11. Negative 3 plus negative 5 gives us negative 8, and so on. In the second example, we're subtracting. 2 minus 9 will give us negative 7. Negative 3 minus negative 5 will give us positive 2, etc. Another operation we may want to do on a matrix is called scalar multiplication. The idea of multiplying a matrix by a non-zero number. So if we have a matrix A that's m by n and a real number C, then CA is the m by n matrix that's obtained when we multiply each entry by C. So in my example, 5 halves times 6 is 15. Negative 3 times 6 is negative 18, and so on. So the multiplication is done in each component of the matrix. It's important to think about what operations are done on matrices. Here's a list of a few of them. The first one is the additive identity law. So any matrix A plus a matrix of all zeros is the same as matrix A. Matrix A plus its negative is the matrix consisting of all zeros. If we have a number A and we want to multiply that by the sum of matrix A plus B, then we get C times matrix A plus C times matrix B. If we have a sum and we want to add that, or we want to multiply that by a matrix, then we get C times A plus D times A for scalars C and D. 1 times a matrix A is matrix A, and 0 times matrix A is a matrix consisting of entirely zeros. Another operation we might want to look at is matrix transposition. So if A is an m by n matrix, then its transpose is the n by m matrix obtained by writing its columns as rows. So the ith column in the original matrix becomes the ith row in the transpose. We denote this by A with a superscript T. So if you look at our example here, matrix A has row 1 consisting of 2, 0, 1, 0. Then matrix A transpose will have column 1, 2, 0, 1, 0. Matrix A has row 2 as 33, negative 22, 0, and 5. A transpose has column 2 equal to 33, negative 22, 0, and 5. A is a 3 by 4 matrix. A transpose, therefore, has to be a 4 by 3 matrix. Now, if we've got m by n matrices A and B, then their sum, if we take the transpose of their sum, it's equal to the sum of the transposes. Similarly, if we take a constant multiplied by a matrix and then take a transpose, that's the same as taking the transpose and then multiplying by a constant. Finally, and unsurprisingly, the transpose of a transpose is the original matrix.